All right. So you could actually, if you want, I mean, it's really your time to ask questions, and I'll try to give you the best answers possible. So whenever you're ready, you can fire away with some questions if you like.
All right. So I'm kind of understanding it for the majority of the part, okay. Except for question 1.29.
Okay. So let's see what we got for 1.29.
And maybe just the answer is wrong in the back of the book, but I'm not sure. So
it's possible. It's possible. So let's see. A container was found in the home of the victim that contained 120 grams of ethylene glycol and 450 grams of liquid. What was the percentage of the ethylene glycol? Express your answer to the ones place. So a container was found in the home of the victim that contained 120 grams of ethylene glycol and 450 grams of liquid. All right. So what I'm thinking is, this would be 1.29. So what I'm thinking is the 450 grams of liquid is the total amount of liquid that is present.
Okay.
So that's the way I'm reading the question, is that it's 120 grams of ethylene glycol and 450 grams of liquid. So I think, you know, my understanding of ethylene glycol would be that ethylene glycol is a liquid. I'm sure they wouldn't expect you to know that. But what I'm thinking is that since it says ethylene glycol in 450 grams of liquid, the 450 grams of liquid would be the total amount of liquid that is present. And
okay.
out of that 450 grams, 120 grams of that is the ethylene glycol. And the rest of it would basically be whatever liquid is present. So
okay.
Based on that, the percentage of ethylene glycol that would be present would be 120 grams over 450 grams, and then we'll multiply that by 100%.
100. Okay.
So when I put that into my calculator.
So I think that's where I got it wrong, that is the total liquid, where other problems you had to add to find that total liquid.
Yes, that's correct.
Okay.
I think a lot of it, so I'm getting 26.67%, and they say they want the answer to the ones place. So,
correct.
Yeah.
27.
27.
And that is the correct answer.
Yeah. So what I'm thinking is that it's basically based on the way the question is, the wording in the question, in the sense that they say 120 grams of ethylene glycol in 450 grams of liquid.
Okay.
So to me, when I see in 450 grams, that means that the total liquid there is 450 grams. And then 120 grams of that would be the ethylene glycol.
Okay.
Yeah, a lot of that is going to come down to the wording of the question, whether you sort of have to add the components together, or, you know, is that the total amount, and is, you know, what they're giving you just a part of it, so to speak.
Okay. And that may be some of the questions I have in chapter 2.
Okay.
But I know there's one in chapter 2 that I don't quite understand.
Sure, go ahead.
And it's about the same. It's 239. So okay. Something about the nines.
2.39.
They're tricking me.
All right, let's see what we got for 2.39. So what I have for 2.39 is complete each of the following metric relationships. Is that
correct? So my question is B.
Okay.
Where we have 1 meter to a nanometer.
Okay. So nano essentially means 1 times 10 to the minus ninth.
Okay.
So essentially, like, you think about some of the units, like kilo means essentially 1,000.
1,000.
Deci means 0.1. Centi
Okay.
means 0.01. So the general idea is that when you have the unit there, or when you have the prefix there, and you take the prefix away, in a sense. So let me see if I can make a little more sense of what I'm saying. If you have 1 kilometer, if you want to take away the prefix kilo, that means that 1 kilometer would be equal to 1,000 meters.
Okay.
Because what happens is that when you take away the kilo, what you substitute in is 1,000. So 1 times 1,000 would be 1,000. So if you have 1 nanometer, that would be equal to 1.0 times 10 to the minus ninth meters. But what they want here is basically they want the other way around.
Okay.
One of the things that's talked about a lot in chapter 2 is the idea of conversion factors.
Correct.
Where you can take any equality and write it in the form of a conversion factor. So this equality right here is the conversion factor that relates nanometers to meters. So if you have 1 meter and you wanted to convert that into nanometers, you would do 1 nanometer over 1.0 times 10 to the minus ninth meters.
Oh, okay.
Because now when you multiply, the meter cancels.
Cancels.
So what you
Okay.
would do here is you would actually divide 1 by 1.0 times 10 to the minus ninth. And what that should give you is 1.0 times 10 to the plus
10
ninth
to the positive. Okay.
nanometers. Correct.
Okay. Yeah, that makes a lot more sense.
Yeah. So that's how, so what they did in that case was they said, okay, you know the conversion between nanometers to meters, but what would essentially 1 meter be in nanometers? So we just have to use this as the proper conversion factor, in this case, to convert 1 meter into nanometers.
Okay, and that kind of brings the connection to all the other conversion factors, which I understand how to set up,
Yes.
but I didn't understand how to go the both way, and now it's connected. Okay.
Yeah. The biggest thing with conversion factors is that, so there are 2 possible conversion factors for any equality. The trick is to use the form that when you multiply, the unit that you're given in the question cancels, and what you're left with is the unit that you need for your answer.
Okay.
That's really sort of the key in doing it and such like that.
Yeah. And you used it in this way of what that whole chart is in the book.
Yes.
And you can set it up as conversion factors. Okay.
Yeah, for any of the units, meter, liter, grams, any of the units of the metric system or the SI system, can be used in this particular way.
Okay. So I think that will help me with my other questions that I have, because I'm missing that connection of how they all tie together and how I can use that to find it. So one question had to go from something with a second.
Sure, if you wanted to look at it.
Okay.
So take a look at it, sure.
It's 2.55.
Okay.
So it's kiloseconds to milliseconds. And I'm like, well, that's not on the chart.
So the way that I would do that one, I see it right here, 55D. So you have here 0.72 kiloseconds, and I'm just going to put that as SEC into milliseconds.
Milliseconds, yeah.
So the way that I would do this one is I would actually do it in 2 steps. I would go from kiloseconds to just
seconds. Okay.
And then I would do seconds into milliseconds.
Okay.
So I would treat it as a 2-step sequence.
Yeah.
So essentially, 1 kilosecond would be equal to 1,000 seconds.
Okay.
Because
kilo means 1,000.
So 1 times 1,000 would be 1,000.
Okay.
Then the other one that I would do is I would start with 1 millisecond is equal to 0.001 seconds.
Or 10 to the negative.
10 to the negative. Yeah, 1 times 10. 1 times 10 to the negative 3.
Okay.
Same thing, absolutely.
Okay.
Now, the other thing, just to point out, and you don't have to do this, but a lot of times with conversion factors, students sometimes don't like to work with fractions or decimals or something like that. So in this case, if we were to multiply both sides of this equality by 1,000, because when you have an equality, whatever you do to one side, as long as you do it to the other, the equality stays true. So if we multiply both sides by 1,000, we end up with 1,000 milliseconds is equal to 1 second.
Oh.
If you wanted to leave it as a decimal or in scientific notation, as long as you do the mathematics right and set it up correctly, you'll come up with the right answer. It's just a lot of times like students don't like to play around with decimals or fractions or even negative exponents in scientific notation.
Correct.
So the way when you have these equalities that have these decimals, the way to get rid of it is multiply both sides by the number that would convert the decimal into 1. So in this case, we want to move the decimal point 3 places.
Yeah.
We multiply it by 1,000.
Okay.
So now we have 0.72 kiloseconds. So based on this equality here, what do you think the conversion factor is going to be to convert?
So it'd be 1,000 seconds over 1 kilosecond.
Very good. And then
so that we could cross off the kiloseconds.
That's right. And then from there, we want to use this equality here.
Okay.
So what form are we going to use now to get rid of the seconds?
The 1,000 milliseconds over 1 second.
That's right.
Okay.
Because now the seconds cancel.
Cancel, and we have what we need.
Yep. So we're going to move the decimal point 3 places. So that's 720. And then we're going to move the decimal point 3 more places. So I believe that comes out to 720,000 milliseconds. As the answer.
Okay.
So sometimes in some of the questions, you'll have to use multiple equalities in order to come up with the right answer. Because sometimes there's not just one that's used. Sometimes you have to use multiple ones. But at some point, you should be able to get from the unit that you're given to the unit that you need in your final answer.
Okay. So I just want to bring this up just because this is how I was doing it.
Okay.
Do we add or subtract exponents?
In terms of multiplying and adding, things of that, like in terms of what?
Yeah. So like if we had 1 second, or that 1 second is 1.0, 10 times to the negative third.
Right.
I'm sorry, 10 to the negative 3 seconds.
That's okay.
And we had another one similar to that, was a 1.0 times 10 to the negative 3. Can we add those exponents?
Okay. So
or no?
Good question. The only time where you can sort of add or subtract exponents is when the coefficients of the numbers in scientific notation are the same.
Okay.
So in other words, in this case, The reason why we can basically add the -3 and -3, and that would give us the right answer of 1.0 times 10 to the -6, is because the coefficients here are both 1.0.
Are the same. But if they're not, then we can't do it.
I wouldn't do that, no.
Okay.
I would basically really tell you to use the calculator in those particular cases.
Yeah, and this conversion factor as well.
Yeah,
so.
Exactly.
Okay.
So, and even if you're not 100% sure and you want to use the calculator, even in this case, I would recommend using the calculator as well. But basically, the only time you can really add or subtract exponents sort of clearly is when the coefficients are the same for the numbers in scientific notation.
And it wasn't taught in the book, so I feel like I was just kind of pulling it from something I've learned, and then I'm like, I think I kind of applied it wrong.
Okay, that's okay. That's okay. That's why hopefully we'll be able to straighten some of those things out as we go along.
Okay. All righty.
All right. Any other questions you might have?
Nope. Let me look.
Okay. If you don't, it's okay. Then I'm just going to go back and do some examples from chapter 1. But if you have others, that's okay as well.
Nope, I think that's all. So like I said, I kind of understand now how to use that conversion factor more efficiently for the problems.
Cool, excellent.
And then I will look at more problems with seeing the volume, the total volume. Oh, I do know there is one. I don't know where it's in my notes. Let me see if I can find it in the book. It has to do with there's like a syrup in the liquid in a container.
Okay, let's see if we can track that one down.
Oh, it's in chapter 2. It is 2.69B.
What is the density of each of the following samples? A syrup is added to an empty container with a mass of 115.25 grams. When 0.1 pints of syrup is added, the total mass of the container and syrup is 182.48 grams. So they want to know the density in grams per milliliter. Oh, all right. Okay, so, all right, couple things. So this is 2.69B. All right. So first off, density, of course, is equal to the mass over the volume. All right.
Correct.
Now, in our answer here, the unit that they want is grams per milliliter. All right.
Correct.
So let's talk about the mass aspect first. So when you have a liquid, can't put a liquid directly on a balance, because if you put a liquid directly on a balance, it's just going to spill all over the place.
Okay.
So one way to get a mass
for
of a liquid is by what is known as weighing by difference. Here's how it works. Basically, you take something empty, like an Erlenmeyer flask or a beaker. These are basic laboratory pieces of equipment. A beaker is like a cup. Graduated cylinder. Graduated cylinder, you see in chapter 2, commonly used to measure volumes, especially of liquids and stuff like that. And what you do is you take that empty container and you put it on the balance and you write down the mass. Now, in this example, the empty container has a mass equal to 115.25 grams. Because they say a syrup is added to an empty container with a mass of 115.25 grams. So then the next thing you would do is you would take your liquid and put it into the container, how much you ever want to measure out. Okay. And what's going to come up on the balance, because you leave the flask, the beaker, the graduated cylinder on the balance, and you put the liquid on into the container, and you're going to get a new mass. So now you have the mass of the syrup and the container. And in this case, the mass of the syrup in the container is 182.48 grams. So with that being said, how do we find the mass of the syrup? Well, if you have the mass of the syrup and the container, and you take away the mass of the container, what are you left with? You're left with just the mass of the syrup. So the mass of the syrup is going to be equal to 182.48 grams minus 115.25 grams. So we get here 3, 2, 7, 6. 67.23 grams would be the mass of the syrup.
Okay.
All right. Now, so that's the mass part. All right. So now the volume. So the volume here, they tell us is 0.100 pints. But in terms of the final density, they want the density in milliliters. So what we have to do is we're forced, in this case, to convert your pints into milliliters. And I wish I remembered all the conversions off the top of my head. That I don't, so I'm going to look back a little bit. And actually, there's only, based on what's in the book, there's really only one equality that we need to use. And that's the fact that 1 pint is equal to 473 milliliters.
Milliliters, okay.
All right. So we'll take the 0.100 pints, and let me just move that down a little bit. So we'll take the 0.100 pints, and we're going to multiply that by 473 milliliters over 1 pint. So we should move the decimal point, I believe, over 3 places. And that would give us a volume of 0.473 milliliters.
Okay.
Did that correctly? Just double check. So 473 times 0.1. Nope, I miscalculated that one. That's why I should use a calculator also.
Yeah.
47.3 milliliters. That makes a little bit of sense. I was going to say that's kind of a small volume. All right. So, because that would give a really high density of a liquid, and that can't be the case. All right. So then now we've got the mass. Now we got the volume. So
we can figure out the density.
All we got to do is divide. 67.23 grams divided by 47.3 milliliters. And that one I'm definitely going to put to the.
Okay. Good. I'm glad I asked that question because, it wasn't the total liquid. It was trying to understand how to find the mass
of
a liquid.
Yeah, the trick there was to know a little bit about weighing by difference, which is really one of the main ways to come up with the mass of a liquid, because the general idea is that, you can't just put a liquid directly onto a balance. You have to empty container on. Some balances, a lot of balances, they have what is known as a zero function, which if you hit that, will set the balance back to zero.
Right.
Container on there. So when you add the liquid, you get the mass directly, but not in this question. In this question, we're definitely looking for weighing by difference.
Okay. That would be the end of my questions.
All right. Great.
As far as I've gotten so far.
That's got pretty far in a short time. All right, excellent. All right, so as I said, I'm just going to go back for the rest of the time this evening and just go through some questions in chapter 10, just to make sure everybody's okay with that. All right, so one of the things they talk about at the beginning of chapter 1, not chapter 10, chapter 1. One of the things they talk about in chapter 1 at the beginning is sort of the scientific method. They talk a little bit about that. Basically, 4 main parts. You have observations. as the term observation implies. It's what you sort of visibly see. You're observing what's going on and you're making notes in a sense about what you're seeing. Something has really caught your eye. It's unique and it's different. And, maybe it's something unexpected and such like that. And sometimes that leads you to question what's going on. And when you question what's going on, that's sort of where a hypothesis comes in. A hypothesis is sort of, as the name implies, a hypothesis really is sort of a question. What if I did this? Or what if I did that? How would this change what's going on? What if I slept more? Would I feel more awake in the morning? Things of that nature. Then how do you test your hypothesis? Well, you test your hypothesis with experiments. If my hypothesis is that if I sleep more, I'm going to feel better. Well, let me, instead of sleeping 5 hours every night, let me sleep 8, 9, 10 hours and see how that makes me feel. And, that's the way we test our hypothesis, is with experiments. And then after your experiments, basically you usually collect some data from that. And that data, which could also be observations as well. Observations can be things that come about not only before an experiment, but during an experiment as well. So that part really is common to, certain areas. An observation might make you question something, and then an observation might give you the answer to something as well. But what do we draw from the data and the observations that we make after the experiment? What we draw from that essentially are our conclusions. I slept 8 hours and I felt more awake. I slept 9 hours and I felt more awake. So what do I conclude from that? I conclude from that sleeping more is helping me feel more awake during the days and such like that. So that's really, in a very small nutshell, the idea of the scientific method. And one of the things the textbook asks students to do is basically look at certain statements and be able to identify them as observation, hypothesis, experiment, or conclusion. So let's take a look at an example of that. And I'm going to try to always pick ones where the answers are not in the back, because I'll leave the answers at the back because you can practice those and check those. So I'll try to do the ones where the answers are not in the back. So let's take a look at 1.10. So 1.10 says, identify each of the following as an observation, a hypothesis, an experiment, or a conclusion. So letter A is that Sally thinks she may be allergic to shrimp. So if you think about that, what type of part, or what part of the scientific method sort of is that? Well, is it an observation? Did she observe that she may be allergic to shrimp? Possibly. Is it a hypothesis? Is it a question? Sally thinks she may be allergic to shrimp. Sounds like a question. She's thinking for whatever reason that she may be allergic to shrimp. Is it an experiment? Well, it's not really something she's testing in a sense. Is it a conclusion? Well, it's possibly a conclusion. But when I look at that statement, Sally thinks she may be allergic to shrimp. If she was concluding something, that statement might read, Sally has found that she's allergic to shrimp. So when I look at letter A, what I'm thinking about letter A is that I'm thinking about a hypothesis. Something has happened to Sally that is making her think that she may be allergic to shrimp. She's not sure. That's why the term think is important, because she's not 100% sure, but she's thinking she might be. So to me, that sort of signifies a hypothesis. So that would be my selection for letter A. Letter B. So yesterday, 1 hour after Sally ate a shrimp salad, she broke out in hives. So, what type of statement is that? Well, definitely not a conclusion. You know, it doesn't answer the question of whether she's allergic to shrimp or not. That seems like where we're heading with this particular question. It's not an experiment. You know, I don't think, you know, yesterday, and this is done previously, so I don't think it's an experiment to see if she was allergic to shrimp, because this was done yesterday. It wasn't done after thinking she may be allergic to shrimp. She broke out in hives. And after breaking out in hives, that was something she probably noticed, that, you know, she ate the shrimp salad and then all of a sudden I got hives. So what type of statement do we have here? You know, to me here, we have an observation. So that's what I'm thinking about 10B, observation. Okay. Letter C. Today, Sally had some soup that contained shrimp. But she did not break out in hives. So to me, this statement actually sheds a little bit of light on letter B as well. And even letter A, because it's really starting to put things together. Yesterday, Sally ate shrimp salad and broke out in hives. Her observation was that she broke out in hives. That led to her hypothesis that she might be allergic to shrimp. So what did she do today? Today, she had some soup. Sorry about that. Today, she had some soup that contained shrimp. So why did she do that? The reason why she did that was to see what the effect would be of having something else that had shrimp in it. So what was she doing? Well, she was basically doing an experiment. You know, she didn't eat shrimp salad again, but this time she ate soup that contained shrimp. And she wanted to see whether she would break out in hives or not. And it turned out that after eating the soup that contained shrimp, she did not break out in hives. So this would be her experiment. And then the last part, letter D, Sally realizes that she does not have an allergy to shrimp. And of course, this statement would have to be our conclusion. That for some reason, after eating the shrimp salad, she broke out in hives. But if she was really allergic to shrimp, after eating the soup that contained shrimp, she should have broke out in hives again. And she didn't break out in hives. So it was probably something else or something else with the salad that caused her to break out in hives. And therefore, when she didn't break out in hives after eating the soup that contained the shrimp, she realized that she doesn't have an allergy to shrimp. So that statement would essentially be the conclusion. All right. So that's one of the things coming out of chapter 1, definitely should be able to do. Look at different statements and identify them as observation, hypothesis, experiment, and conclusion.
So on the homework, I think that's where I got 2 of them wrong, was this area.
Okay.
and you use up so many chances to move the information. Can we go back and check on that? Can we find the answers, or is it just something we need to talk to you about in the Zoom?
That's a good question. I'm not 100% sure how. It's my first time using like the online mastering.
Okay.
I would think that you would be able to see what the answers are. So
okay.
When you go back into the mastering, it doesn't show you what the right answers are.
I didn't go back into it.
Okay.
It just said that I had used up all the attempts,
okay.
And then,
So what I would say is go back in, see if you can see what the right answers are. If you can't, let me know. And then I'll look at the questions and we'll have to figure out a way to, after everybody is submitted, after the due date, and everybody submits, then we'll have to figure out a way to go over the right answers. Because I think that's part of the learning process. It's my first time using that. I don't know all the ins and outs just yet, but I would think that at some point, maybe after it's due, the right answers will be available. So we'll make sure of that, and I'll follow up as needed. Absolutely. All right. All right. Let me also talk a little bit about scientific notation, because I know a lot of times these days it's all about the calculators and such like that. But, I do think it's important to a certain extent to know a little bit about numbers in scientific notation and such. So when you have a number in scientific notation, there are two parts. There is a coefficient and there's a power of 10. Now, the coefficient is usually a value between 1 and 10. Doesn't have to be. Sometimes students, myself, will write coefficients that are larger than 10, smaller than 1. But the general idea with scientific notation is that the coefficient is usually a value between 1 and 10. So, for example, if you had the number 24,000 meters, how do we come up with the coefficient? Well, basically what you want to do is you want to move the decimal point in the number to give a value between 1 and 10. Now, a lot of times whole numbers won't have decimal points associated with them. So if there's no decimal point given for a whole number, in the world of scientific notation, when we're trying to figure out how to put a number in scientific notation, we can put one in at the end. Now, in this case, what I'd want to do is I'd want to move the decimal point to the left 4 times. Because when I move the decimal point to the left 4 times, I now have a value between 1 and 10. And that value is 2.4. Because if I moved it once, that takes me from 24,000 to 2,400. If I move it twice, 240. If I move it 3 times, 24. If I move it the 4th time, 2.4. So in this case, 2.4 would be my coefficient. So that's going to be then times 10 to some power. Now, the number of times we move the decimal place gives the power of 10. But the one thing to keep in mind is that the power of 10 can be positive or negative. And the trick to know which one it is, if it's positive or negative, essentially is the following. If the given number is larger than the coefficient, the power of 10 is positive. So in this example here, and it's really not a trick question, which is the larger value? Is it the given number 24,000 or is it the coefficient 2.4? 24,000 is much larger than 204. So that means the power of 10 has to be positive. Now, again, how many times do we move the decimal place? We move the decimal place 4 times. So in our example here, to be written in scientific notation would be 2.4 times 10 to the positive 4th meters. Or you can leave out the sign if the power of 10 is positive, 2.4 times 10 to the 4th meters. Okay. So that's how we know when the power of 10 is positive. On the other hand, if the given number is smaller than the coefficient, the power of 10 is negative. So I'll show you an example. 0.00014 liters. So in this case, to get the coefficient, I'm going to move the decimal point to the right 1, 2, 3, 4 times. Because when I move it 4 times, that gives me a value between 1 and 10. So for this example here, the coefficient would be 1.4. Now, I move the decimal point 4 times again. But in this case, is it 10 to the positive 4th or is it 10 to the negative 4th? So which is larger, the given number or the coefficient? In this case, the coefficient is larger. 1.4 is larger than 0.00014. And therefore, in this case, the power of 10 is negative. So that would be 1.4 times 10 to the minus 4. So essentially, that's how we take a number and we make it into scientific notation. To go the other way, from scientific notation into a number, if the power of 10 is positive, that would mean to move the decimal point to the right. And if the power of 10 is negative, that would mean to move the decimal point to the left.
And why does the liter and the meter go after the 10? Like, why doesn't it go 1.4 liters times 10 to the negative 4th?
The main reason why is because essentially it's not 1.4 liters, it's 0.00014 liters.
Okay.
So to me, and I've seen other students do that as well, and usually I correct them on that because to me, the unit should always go after the entire number. And that 1.4 times 10 to the minus 4th is the entire number. Okay. Number and then unit associated.
And unit. Yeah, okay. And that isn't 1.4 liters. So yeah.
Yeah, that would be my main rationale for it. Okay. But I've seen other students do that as well. Yeah. I've corrected them on it a little bit. The other thing I want to mention is with negative exponents. Sometimes this causes a little bit of an issue. And that is the larger the negative exponent, the smaller the number. Because the larger the negative exponent, the more times we're going to move the decimal point to the left, the smaller the number is going to be. So, for example, and this is in, this would be something similar to like what's in 128. You know, they give you two numbers. You know, if you had something like 7.9, I'm just changing it a little bit, times 10 to the minus third, or 5.5 times 10 to the minus ninth, which one is the larger number? Which one is the smaller number? Something to the minus ninth power is much, much smaller than something to the minus third power. So the 7.9 times 10 to the minus third would be the larger number. And the 5.5 times 10 to the minus ninth would be the smaller number. And just off the top of my head, one of the reasons why being able to do this with numbers, being able to tell with negative exponents, which is the larger and smaller number, is that when we get to chapter 10 with acids and bases, you know, one of the things that'll be talked about is how to tell whether a solution is acidic or basic. And the two numbers you're going to have to compare are both going to be numbers in scientific notation with negative exponents. And at that point, it's very critical to be able to figure out which is the larger number, which is the smaller number. So that's why I just wanted to mention this in terms of the negative exponents. The larger the negative exponent, minus 9, 9 is larger than 3, the larger the negative exponent, the smaller the number. So I definitely wanted to mention that as part of the discussions this evening. All right, let me just see what else is in chapter 1. Looking at, yeah, they do a little bit. I'll just do one or two algebra problems, because sometimes there is going to be some mathematics involved. I'm not so much worried about the adding and subtracting and dividing and multiplying, because I think the calculator will help with all of that. But I do just want to do a couple of the algebra problems to be able to solve. So first one they have is 2b plus 7 is equal to b plus 10. All right. So one variable problems, basically what we want to do is we want to get the variable on one side and the non-variable numbers on the other side. So to do that here, and I'll just really take it step by step, what I'd want to do is I want to get the b's on the left side, and I want to put the numbers on the right side, because basically what I want to do is I want to keep the variable positive. So the way I would move this b to the left side is that I would subtract both sides by 1b. Because if there's no number in front of the b, that means 1. So I would subtract both sides by 1b. So when I do, that cancels out. So I have 1b plus 7 equals 10. And now to get to the 7 to the other side, I'll subtract both sides by 7. Because remember, again, with equalities, whatever you do to one side, as long as you do it to the other, will be fine. So the 7s cancel out, they add up to, I shouldn't say cancel, they add up to 0. So you get 1b is equal to 3. So therefore b is equal to 3. And we can check that out. 2 times 3 plus 7, 6 plus 7 is 13. And then b plus 10, 3 plus 10 is 13. So that works out to be perfectly okay. All right. And then for letter B, so that was A. For letter B, they have 3b minus 4 is equal to 24 minus b. All right. So for this one here, the first thing I would do is I would add b to both sides. So that adds up to 0. So for this side, we get 4b minus 4 is equal to 24. And then to get the 4 to the other side, the right side, I would add 4 to both sides. So minus 4 plus 4 adds up to 0. So I get 4b is equal to 28. Now, how do I solve for b itself? Now I'm going to divide both sides by 4. So 28 divided by 4 is 7. So in this case, b would be equal to 7. And we can check that. 3 times 7 minus 4. 21 minus 4 is equal to 17. 24 minus 7 is equal to 17. So therefore, that adds up to be, that turns out to be correct. Okay. And then just to show you one other example, 21b, they give you a over 6 equals 7. So remember, in this case, what would you want to do to solve for a? Let's write 7 as a fraction. So how can we write any number as a fraction? We can write any number as a fraction by putting it over 1. And then what's the correct operation when you have two fractions separated by an equal sign? When you have two fractions separated by an equal sign, the correct idea is to cross multiply. So a times 1 would be equal to 7 times 6. And therefore a is equal to 42. And the way we would check that basically is that 42 divided by 6 turns out to be 7. All right.
Could you do one more?
Sure. Did you have one specifically in mind, or?
Yeah, let me look for it.
Yeah, go right ahead, please.
It's when you have like a fraction like that, but you're trying to find, so you have the 42 and you're trying to find the 6. Can we just rewrite that question?
Sure. I think I
to 42 over a?
So 42 over a is equal to 7.
7, yeah.
Okay, so again, I would do the same thing. Put the 7 as a fraction by putting it over 1. Because again, when you have two fractions that are separated by an equal sign, the thing we'd want to do is we want to cross multiply. So in this case, what I would have is 42 times 1 is equal to 7 times a. So 42 times 1 is 42. 7 times a is 7a. So to solve for a, we'd want to divide both sides by 7. So the 7s cancel out. 42 divided by 7 is 6.
That's 6. Okay.
That's your answer for that one. Yeah.
Yeah, I knew it was division, but I didn't know how to set it up.
Yeah. So basically, when you have examples like this, where you have a fraction on one side, but not a fraction on the other, make the other side into a fraction, because then that should trigger when you have two fractions separated by an equal sign. The correct thing to do would be to cross multiply.
Okay.
You cross multiply. Trying to think of anything else. Yeah, so just looking, 44, you have minus 95 minus negative 11. Whenever you're subtracting a negative exponent, but not a negative exponent, negative number, it becomes plus positive. So it would be minus 95 plus positive 11. So that turns out to be negative 84, I believe. And
yeah,
I might have to just double check. So used to using my calculator these days. 95, where are you? Negative plus 11. Yeah, negative 84 for that one. Yeah, so when you're subtracting a negative number, just change that into plus positive. A couple of things, when you multiply and divide, if you have a positive times a positive, or a negative times a negative, or a positive divided by a positive, or a negative divided by a negative, each one of these, the answer is going to be positive. And then basically whenever you have positive times negative, or positive divided by negative, or negative divided by positive, then in these cases, the answer is going to be negative. So when you multiply and divide, if the signs are the same, the answer is always going to be positive. But if the signs are different and you multiply or divide, the answer is going to be negative. And I think that's about what I was going to discuss. All right. Any other questions?
No, that was good.
All right. Excellent. I appreciate you joining. Next week, we'll cover more basically of chapter 2. I'll post that in the week 2 announcement and such like that. And, this is sort of how it'll go. But, as if you have chapter 3 questions, and there's nobody else sort of around, we can, we'll answer any questions that you might have as well. So
yeah, I'm going to do more of chapter 2.
Yeah.
But I just wanted to make sure I was trying to understand it. And I didn't quite sure how far we could ask. So
yeah, the goal sort of is to stay within the chapter.
Yeah.
But I think that'll be a little bit easier as the chapters go on, because I think you'll have more and more questions per chapter as the chapters go on. So
correct.
Absolutely. All right.
Okay.
Nice meeting you.
Yep. Thank you.
Stay well. See you next week.
Bye.